Welcome to this explainer. All right, let's dive into a really fun scientific mystery that's probably happening right in your own bathroom. What exactly is the fizz coming from a bath bomb? I mean, we've all seen it, right? You toss this dry, powdery little sphere into a tub of water and bam, it erupts into this crazy, satisfying frenzy of bubbles. But, we're not just here to sit back and watch the show. We really want to get into the mechanics behind the magic. We're going to play detective.
So when that bath bomb hits the water and starts fizzing, have you ever stopped to wonder what that fizz actually is? It's not just trapped air escaping. It's actually a brand new, completely invisible gas being created right there in real time by a chemical reaction between the bath bomb ingredients and the water. And that presents a pretty awesome detective story for us. How on earth do we identify a substance that we literally cannot see with the naked eye? I mean, we can't hold it, we can't just toss it on a scale. So how do we solve this?
Section 1. Fingerprinting and visible gases. Okay, just like real detectives use unique fingerprints to identify suspects at a crime scene, scientists use specific physical properties to identify invisible gases. Every substance in the universe has these core characteristic properties that just stay true no matter where you test them. Our first crucial fingerprint here is flammability. Basically, how does this stuff interact with fire? Some gases are super reactive and will literally explode, others will smother and put flames out, and some just totally ignore fire altogether. Testing this is going to give us a massive clue.
Our second fingerprint is density. Think of this as how tightly packed the particles of the gas are in a given space. And here is the golden rule for our investigation today. Fluids, and yes, gases totally count as fluids, behave predictably based on their density. Less dense gases are always going to float upward, while denser gases sink right downward.
All right, here is our initial suspect list. We've compiled data on 10 common gases, running all the way from hydrogen to butane. And you'll notice a really wide variance in their densities and how they react to fire. By testing our mystery bath bomb gas to see if it floats or sinks, and whether it bursts into flames or smothers them out, we can logically start crossing names off this massive list until we catch our culprit.
Section 2. Establishing a baseline.
Now, before we go testing the unknown suspect, we have to prove our testing method actually works, right? We need to make sure our eventual test on the bath bomb is perfectly accurate. So we're going to test a gas we already know, helium. Here's how we set up our baseline experiment safely. Step 1, we take a standard pre-filled helium balloon and carefully snip the bottom open to insert a straw. Step 2, we stick that straw into an inverted, meaning upside-down glass flask. And step 3, we just trap the gas in there with a rubber stopper. We're essentially manually moving the helium from the balloon into our test container. But this brings up a really fascinating challenge. We are releasing this helium gas into that downward-facing glass flask, but the gas itself is completely invisible. So when we eventually pull that stopper out, how can we be absolutely certain the helium actually floated up into the base of that upside-down flask, instead of just sinking and spilling all over the table? Which leads us to a really crucial question. How do you measure something you can't even see? We desperately need a secondary way to detect the location of this invisible helium. We have to actively prove that it is in fact less dense than the room air, and that it floated upwards just like we predicted. Basically, we need a detector.
And this brilliantly illustrates our payoff. We use our flammability fingerprint as the detector. It turns out a match stays perfectly lit when held directly under the open upside-down flask. Why? Well, because the lighter helium is safely trapped way up high inside the glass. But the very second we flip that flask upright and place a lit match over the top opening, boom, the flame instantly goes out. The less dense helium rushes up out of the top of the bottle and suffocates the flame. So our baseline is established. The test absolutely works.
Section 3. Testing the unknown gas.
First, a quick but super important word on safety. You've got to follow strict protocols here. Since we are generating the bath bomb gas in a regular plastic soda bottle instead of a lab-grade glass flask, we absolutely must keep our open flames at least an inch away from the plastic. The goal here is to test the gas, not melt the bottle and create a completely different kind of mess.
Okay, here is our really ingenious experimental setup for the unknown gas. Step 1, we seal some mini bath bombs in water inside the plastic bottle to build up a nice concentrated amount of our mystery gas. Step 2, we light a small candle and put it in a pan directly below the bottle. And step 3, we take the cap off and gently tilt the bottle sideways. The whole trick here is to carefully pour the invisible gas out of the bottle and over the flame, without spilling a single drop of the liquid water that's still inside.
And here is the dramatic result. The invisible gas pouring from the bath bomb bottle completely extinguishes the candle flame placed below it. Guys, this is a massive breakthrough. Unlike the helium which floated up to put out a flame above it, our mystery gas clearly traveled downward out of the bottle and smothered the candle resting below.
Section 4. Arguing from evidence.
Now for the fun part, using logical, scientific reasoning to narrow down our suspects based on this new physical evidence. Let's compare the behavior of these two gases. Our known gas, helium, put out a flame above it, which proves it floats. Our unknown bath bomb gas put out a flame below it. Because this gas successfully flowed downward out of the tilted bottle to kill the candle, it absolutely 100% must be denser than the surrounding room air.
Let's look at the hard numbers for a second. Normal room air has a density of roughly 1.160 grams per liter. Because our culprit sank right through that room air, it mathematically must have a density higher than this 1.160 threshold. Honestly, anything with a density lower than 1.160 would have just floated upward and left our candle burning happily.
So it is time to deliver the verdict. Let's look back at our list of 10 suspects. We can immediately cross off any gas that is flammable, right? Because our gas put out a fire. Then we eliminate any gas with a density lower than 1.160 grams per liter. By applying just those two fingerprints, we successfully slice down our massive initial list to just these three non-flammable heavy gases: nitrogen, argon, and carbon dioxide. We have scientifically proven that the fizz has to be one of these three.
We've narrowed it down to 3 final suspects. But what future property test could finally crack the case? If density and flammability got us this far, I want you to really think about what other physical properties or cool experiments might isolate the single true identity of that fizz. Keep that curiosity alive, and we'll see you in the next explainer.